It's smaller than your refrigerator, it's older than your parents, it's traveling faster than a rifle bullet, and right now it is so far from you that a radio signal moving at the speed of light needs over 19 hours just to reach it. It carries less computing power than the key fob for your car, and somewhere out past the edge of everything the sun protects, it is listening to a sound that no human ear has ever heard before, a low, persistent hum coming from the space between the stars. That object is Voyager 2. And before this video is over, you're going to understand why the frequency it just picked up isn't science fiction. It's real data from a real spacecraft that is quietly rewriting what we thought we knew about the edge of our solar system. Stop and sit with that for a second. This isn't a signal beamed at us, it's a signal Voyager 2 is standing inside of, out where almost nothing human-made has ever gone. Quick pause if you're new here. This channel breaks down real space missions, the ones NASA doesn't always explain in plain English. No hype, no fiction, just what the data actually says. If that's your kind of thing, subscribe now, because what happens later in this video, involving a very specific date in the near future, might be the most important thing this spacecraft ever does. Let's go back to where this all started. 1977, Voyager 2 launched first that year, on August 20th, followed weeks later by its twin, Voyager 1. Back then, the mission had one job: fly past Jupiter and Saturn, take pictures, measure some radiation, and call it a career. That was the entire pitch. 4 years, 2 planets, done. But NASA had noticed something rare happening in the sky. Once every 176 years, the outer planets line up in a way that lets a spacecraft use each planet's gravity to slingshot toward the next one, saving decades of travel time and fuel. Engineers realized they could ride that alignment all the way from Jupiter to Neptune if the hardware held together long enough. They called it the Grand Tour. It was ambitious, expensive, and, by the standards of 1970s engineering, borderline reckless. Nobody expected Voyager 2 to still be transmitting data half a century later. Nobody expected it to survive the radiation belts of Jupiter, let alone the vacuum and cold of interstellar space. The mission plan didn't even include Uranus and Neptune as a promise. Those were bonus objectives, dependent on the spacecraft simply not breaking first. It didn't break. Not at Jupiter, not at Saturn, not anywhere. And it kept exceeding expectations at every single stop. At Jupiter, it found active volcanoes erupting on the moon Io, the first time humanity had ever seen volcanic activity anywhere besides Earth. At Saturn, it revealed the staggering complexity hidden inside those rings, structures far more intricate than any ground-based telescope had ever shown. Then it did something no spacecraft has done before or since. It flew past Uranus in 1986 and Neptune in 1989, making it the only spacecraft in human history to visit all 4 giant planets in a single mission. At Neptune, it discovered geysers of nitrogen ice erupting from the moon Triton, a moon so cold that scientists still don't fully agree on why it's geologically active at all. Then, planet by planet, the targets ran out. And Voyager 2 just kept flying, out past Pluto's orbit, out past where sunlight fades to almost nothing, toward a boundary nobody had ever crossed with a working machine. But none of that prepared anyone for what came next. Here's the first major turning point in this story, and it happened on November 5th, 2018. That's the day Voyager 2 crossed something called the heliopause. Think of the sun as a campfire on a cold night. The heat and charged particles from that fire push outward in every direction, forming a bubble around it. And that bubble is called the heliosphere, and it's made of solar wind, a constant stream of particles blasting outward from the sun at hundreds of miles per second. The heliopause is the edge of that bubble, the exact point where the sun's influence finally runs out and the ancient, cold material between the stars takes over instead. Scientists had a rough idea of where this edge might be because Voyager 1 had already crossed it back in 2013. But one crossing is one data point, and one data point can always be an outlier. Every second crossing is a chance to either confirm the discovery or completely undo it. This is where it gets personal, because of what almost went wrong. Voyager 1's plasma science instrument, the one specific piece of hardware built to directly measure the density and behavior of charged particles around it, had failed years before that spacecraft ever reached the boundary. It was blind at the exact moment it mattered most, forcing scientists to infer the crossing indirectly, through other instruments, rather than measure it head-on. Voyager 2 was not blind. Its plasma instrument was still alive, still working, and when it crossed the heliopause, it caught something Voyager 1 never directly could, a 20-fold jump in particle density, all happening across a distance smaller than the width of Earth's orbit around the Sun, 20 times denser, almost instantly. Imagine walking through a doorway from a silent room straight into a packed stadium mid-roar in a single footstep. That's the scale of what Voyager 2 measured, and it gave scientists their first direct, unambiguous confirmation of exactly where the sun's protection ends and true interstellar space begins. Why does that matter to you? Because everything you've ever touched, every person you've ever loved, every war, every book, every sunrise in the history of our species, all of it happened inside that bubble. Voyager 2 became only the second human-made object in all of history to physically leave it. Here's the second turning point, and this is the one the title of this video is really about. Voyager 2 carries an instrument called the plasma wave subsystem. It doesn't take pictures, it doesn't need eyes. What it does is listen, it detects the natural vibrations, the oscillations, moving through the charged particles surrounding the spacecraft. Scientists can convert those vibrations into an audio frequency, and when they did, using data gathered on January 30th, 2019 in the interstellar medium, they picked up a persistent, structured tone, not random noise, not electronic interference. A steady oscillation generated by the plasma itself, coming from material that has existed in the space between stars for far longer than our solar system has existed at all. This wasn't an alien broadcast. It was something arguably stranger, direct proof that the space between stars isn't silent and isn't empty. It has structure, it has rhythm, and scientists can now use that rhythm like a cosmic thermometer, measuring the density and behavior of a region of space that no human instrument had ever sampled directly before. University of Iowa's Don Gurnett, the scientist who led the plasma wave investigation on both Voyager spacecraft, put it plainly when this data came back. In his words, the old assumption that the solar wind simply fades away gradually the farther you travel from the sun is simply not true. There is a wall, a boundary, a measurable line in space, and Voyager 2 proved it not once, but twice, from two completely different angles of approach. Science Daily, think about what that means for you, sitting wherever you're sitting right now. For your entire life, and for the entire recorded history of human civilization before you, we assumed the edge of the sun's influence just trailed off, like fog dissolving into open air. Voyager 2 proved it's actually a hard boundary, almost like a coastline, with waves of interstellar plasma breaking against it in real, measurable jumps. That's not a footnote in an astronomy textbook. That's a fundamental correction to how humanity understood the shape of its own cosmic neighborhood. Here's the third beat, and it's about location, not just numbers. Voyager 1 crossed into interstellar space through the nose of the heliosphere, the leading edge, the part pushing forward through the galaxy as the entire solar system moves. Voyager 2 crossed through the southern hemisphere of that same boundary, a completely different region, years apart and in a different direction entirely. That gave scientists something they had never had before in the history of this science: two independent measurements from two different points around the same bubble, taken by two different spacecraft. And the readings matched. Not roughly, remarkably closely, about 0.055 particles per cubic centimeter, where Voyager 1 broke through in 2013, and about 0.039 where Voyager 2 broke through in 2019. Two different machines, two different locations on the boundary, two different years, and the interstellar medium answered the same fundamental way both times. That's not a fluke, that's confirmation. That's science working exactly the way it's supposed to, one lonely, uncertain data point becoming a real, repeatable, trustworthy pattern. Here's the fourth beat, and it's the one that's still unfolding. That hum Voyager 2 detected isn't a one-time event. Follow-up research using Voyager 1's data found that these plasma oscillations are essentially continuous, persisting for years at a time rather than flaring briefly and vanishing. That persistence let scientists build something new, a rough, ongoing map of how plasma density changes as you move deeper into interstellar space, far from any star at all. It turns out that density isn't flat and uniform out there. It rises gradually the farther the spacecraft travels from the heliopause, suggesting the interstellar medium itself has its own internal structure, shaped by forces astronomers are still working to fully understand. In other words, the empty space between stars has weather, it has geography. Voyager 2 is the machine currently mapping it, one signal at a time, from a region of the galaxy where nothing else humanity has ever built can currently reach. If this kind of thing gets you fired up, a 50-year-old machine still teaching us new physics from another region of the galaxy, hit like on this video right now and drop a comment telling me what you think that Hume in interstellar space actually sounds like to you. I read every one, and some of the best video ideas on this channel started in that comment section. Now let's talk about the people behind this, because it's easy to forget there were human beings holding their breath through all of it. This mission has outlived most of the engineers who originally built it. Some of the scientists who designed Voyager's instruments in the 1970s have died of old age while the spacecraft they built kept flying, kept transmitting, kept outliving them. The Voyager program's chief scientist for nearly 5 decades, Ed Stone, guided this mission from the first Jupiter flyby in 1979 all the way to the edge of interstellar space, only retiring after watching data trickle back from a distance so extreme it takes nearly a full day for a radio wave to make the round trip. Every single power decision on these spacecraft today is a gamble with no do-overs. There's no repair crew, there's no backup mission waiting in the wings. If a command is sent in the wrong order, if a heater is switched off at the wrong moment, the mission ends instantly, over 19 billion kilometers from anyone who could ever fix it. The team spends months simulating a single maneuver before they dare send it, running every possible failure scenario in advance, because out there is no such thing as trial and error. There is only the first try, and it has to work. That fear, that caution, that decades of careful, patient labor, it's happening again right now, in 2026. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, essentially chunks of decaying plutonium slowly converting heat into electricity as the radioactive material breaks down. That power source doesn't get refueled. It only shrinks by roughly 4 watts every single year, a slow and unstoppable countdown that started the moment each spacecraft left Earth. Since 2024, mission engineers have been forced to shut down instruments on both spacecraft just to keep the rest alive, one hard sacrifice at a time. Voyager 1 is already down to just 2 working science instruments. Voyager 2, as of this year, was on track to lose one of its last 3 before 2026 came to a close. So on August 4th, 2026, NASA engineers executed a maneuver they nicknamed the Big Bang, a simultaneous, synchronized swap of power-hungry components for lower power alternatives, switching off aging heaters and an outdated tape recorder while keeping the spacecraft precisely warm enough to survive the swap. One miscalculated temperature, one frozen fuel line, and Voyager 2 goes silent forever, with no way to ever know exactly what went wrong. It worked. All 3 remaining instruments on Voyager 2 are still transmitting today, and engineers now believe that same technique, tested successfully out there in interstellar space, will be applied to Voyager 1 next, buying both aging machines at least another year of scientific life. Let that sink in. This isn't a story from the archives. This happened this year, and it's still playing out as you watch this video. And there's a specific milestone worth marking down right now. Voyager 2 launched on August 20th, 1977. That means on August 20th, 2027, this spacecraft will officially reach 50 years of continuous operation, half a century, spent doing a job that was only ever designed to last 4. No spacecraft in human history has operated that long, that far from home, while still returning usable scientific data from beyond our solar system. Engineers are openly stating their goal is to keep at least one instrument alive on each Voyager probe deep into the 2030s. If they succeed, we may be looking at the first machine built by human hands, still listening to the universe 60 years after it left the ground. Zoom out for a second, because this is bigger than one spacecraft. Voyager 2 is a message we sent to ourselves before we fully understood what we were even asking of it. It was built to visit 2 planets. It ended up mapping the literal edge of our solar system, discovering that the boundary between us and everything else isn't a gradual fade, it's a threshold, sharp enough to measure, real enough to cross, and structured enough to hum. Every civilization that has ever looked up at the night sky has wondered where the edge of things might be. We built a machine in the 1970s, with less computing power than a modern calculator, and it actually found that edge. It's out there right now, powered by decaying plutonium, running on borrowed time, still working, still listening, still sending data home across a gap so vast that light itself needs over 19 hours to cross it. And somewhere on that spacecraft is a golden record, recordings of Earth, its languages, its music, its sounds, sealed and sent outward on the off chance that something, someday, finds it. We built our own message in a bottle and set it adrift in an ocean with no known shores at all. But here's the question nobody can answer yet, not NASA, not any scientist working this mission today. That hum Voyager 2 picked up in the interstellar medium, the plasma oscillations, the structured signal drifting through the space between stars, we understand roughly how it's produced. But we don't fully understand why it persists the way it does, steady and structured across such enormous stretches of space and time, or exactly what that tells us about the deeper shape and turbulence of the material filling the gaps between every star in this galaxy. We are, right now, hearing something real, coming from a place no human instrument had ever sampled directly before Voyager 2 got there, and we are still working out what it's actually telling us. If this story pulled you in, subscribe and turn on notifications, because this channel covers missions exactly like this one, the real ones, backed by real data, not speculation. Drop a comment and tell me if you'd want to hear what that interstellar hum actually sounds like, because I might make that its own video. Share this with someone who needs a reminder that a 50-year-old machine, smaller than your fridge, is still out there teaching us things about the universe we live in. And next time, we're going deeper into the Voyager Golden Record, what's actually on it, why it was chosen, and what it says about us to anything or anyone that ever finds it.